That last chapter somehow tried to handle that one, which was a very realistic problem that you have in practice. Now the thing here is that in this part, what we want to do, first we want to just talk about PGM, but this time we are going to use an estimate of the value, a kind of useful estimate of the value to update. So first we do that, but then at the second part of the chapter, we talk about the discrete policy gradient approaches, which are a bit different. So you can think of them like you get back to chapter 4. Yes, exactly the last part which I gave you as an introduction. So I told you, like, if you have a network which can find the optimal action, you can just feed that optimal action to your Q network and you compute the value of that, right? So that one was not too dummy. I mean, actually, we can implement that, and that is the idea of deterministic policy gradient methods. The most famous algorithm is DDPG, which you might have heard in robotics. Many people use that. So that is the second part that we're going to talk about. So let's first start with the first part, which is basically what we know. So I guess we had this kind of division at the very first. So I told you that we have two different approaches in general for reinforcement learning. Some of them are based on the value. Some of them are based on the policy. So here, when you do value-based approaches, you're basically going with approaches where you directly work with the value or action value. So SARSA and Q-learning are the most famous ones, and when you implement them using function approximation, then you are basically doing deep value-based reinforcement learning. You can do, so these are approaches which use deep value networks. You can use also the policy network, right? Directly work with the policy. And in this case, we had a bunch of different approaches. The most essential ones, the most, say, practical ones are TRPO and PPO. And these are approaches which directly update the policy network, right? And then when we talk about the actor-critic, we talk about a mixture of them. So you have a value network which is taking care of value estimation for you, and you have a policy network which takes care of updating. Now, from a kind of theoretical point of view, there are not too much things that you need to add. I mean, basically what you learn, you can simply extend it here. There are, however, some practical tweaks, which we're going to talk about them. So first of all, why people call it actor-critic? Because actually people they wanted to just make it more interesting. And then they would say that the policy network is essentially the actor, right? So you get this state, you look at this state that you are, and you are going to sample from this policy network, right? When you sample from this policy network, you basically get an action, so you are the actor. The policy network is the actor, right? So it is going to act based on the particular state that it sees, and then if it acts, then it wants to update its own policy. When it wants to update, it needs to know what is the value of the action that it has done, right? So it's going to take a look at that action value pair and then compute or estimate the value. And based on that one, it's going to just update its own policy, right? Because you do know that the gradient is going to depend on the advantage term, which is computed in terms of those values, right? And now the point is that if you have a value network, it's like a kind of expert or critic who is sitting there and is looking at what you are doing and giving you some value, right? You did a bad job, you did a good job, right? And based on that, you are going to play with the weights in the policy network, right? So it's somehow providing you a sort of critic. And yeah, people thought something like this, like you are the actor who is playing the game, and this guy is the expert who knows how to play. And every single action that you do, the critic is going to give you some feedback, right? You did a wrong action, don't do that next time, and you are going to reduce the probability of that action and increase the probability of other actions. And of course, you do it through gradients, right, within your networks. But intuitively, you're somehow doing that. Now, one thing that might worth mentioning is that for many people, policy gradient method and actor-critic are the same. So if you see someone who has not been in this lecture, might tell you, well, PGM is actor-critic, right? But this is not true. I mean, practically that's correct because they give such, if they have been a bit, they have put a bit of thought behind it, not simply taking it from internet. So they might claim something like this, that if you want to implement a PGM at the end of the day, you need to know the advantage, you need to know the values. And this means that you need a value network to estimate that. And this is practically correct, but as I told you before, you can do all the estimation also by Monte Carlo, right? And this is not going to be promising. This is not going to function in realistic problems, but, well, you can do it. So theoretically, PGM is not actor-critic if you want to be very precise. But, and we have reinforced algorithm, which is a pure PGM, right? It does not use any value network, right? So this is a kind of one of those twists or one of those kind of conceptual questions that you can find out whether someone has understood reinforcement learning or anything based on simply just getting information from internet, or they have just educated themselves in the topic. So yeah. Now let's just start by implementing PGM. So up to this point, whenever we wanted to just compute something inside PGM, I always told you when we get into this value network, I told you that we have this value network, right? I write you value network V, right? V of that particular policy, and we compute that. Using that one, we can sample the advantage, right? So we talked about this, and I always show you this V pi theta. I never told you how exactly you can compute this one. Now, you can guess that I want to put a neural network here. That's correct, but let's start doing it step by step. Say I am just doing one PGM. If I am doing PGM, it doesn't matter what kind of PGM I am implementing. At the end of the day, I always need to have this utility, right? This advantage term, right? Either if I do baseline, if I do TRPO, if I do PPO, I always use the same guy, right? Maybe I play with it using importance sampling, but at the end of the day, I'm using the same sample, right? And if I want to compute that guy, this is the immediate reward that I get every single time, plus next value at the next state minus the value at my current state, right? And yeah, the value function V pi is actually the policy, the value of the policy that I am playing with. So one thing which I guess I have indicated enough number of times, and I'm pretty sure you just see it immediately, is that we cannot think about having one value network which has been trained completely independently, and then we use it only for estimation, right? Because our policy, when we are doing policy gradient, is changing every iteration, right? You change the parameters, this means that the policy is changing. When the policy changes, the value function is changing as well, right? So you cannot train something offline and then use it, right? Definitely you need to train it online along with your policy, right? Because this is the guy who is predicting the value of your own policy, right? And the policy is changing, that guy is changing as well. So don't do this mistake that, yeah, we evaluate that guy, train something for evaluation, and we keep it forever. This is not possible. This is not correct. So that was the algorithm we had, right? For example, this is the advantage policy gradient method. This is the basic baseline approach. We are not doing any TRPO or PPO yet here, so there is no trust region required. And then what we compute, or the bottleneck right now is line number 7, right? In the line number 7, I cannot compute that sample. I cannot simply take that sample, right? So if I want to just compute that guy efficiently, how can I do that? Well, I can start thinking again from scratch, thinking of having a mini batch of trajectories. And based on that mini batch, I try to estimate my value. I do know this is not going to work, but it's going to give you a bunch of labels, which we use later to just train our value network, right? Now, do you have any idea how I can estimate this guy if I just collect a trajectory? One trajectory. If I have one trajectory and I want to use Monte Carlo to estimate, how can I do that? I go over my trajectory, I see how many times the same state has happened, and then I just compute the sample return. I average them. This is going to be Monte Carlo estimate, right? And if I have a mini batch, I can just average also over the mini batch. So this is the trajectory that I have, right? This is one sample trajectory. And the thing that I'm going to do, if I want to know what is the estimate of the value for ST, right? So one estimator that I have is the sample return, right? I would say S1 is happening. So R due towards the end, these are the things that I have collected, so I'm going to add them up. This is the sample return, right? This is the sample return for state ST, right? And now, if I want to know what is the estimator of the value of one particular state, so I just need to know how many times this state has happened inside the trajectory. This is exactly the same thing we did in chapter 3. And yeah, that's the same thing, right? I'm going to say the estimate of the value for one particular state S is actually the number of times that ST, my state, has been S, right? I'm going to add them up. This is the number of cases happening. I am also going to divide it by the number of samples I have in my trajectory, and I'm going to average the values for every single of them, right? So if the same state happened first and somewhere in the middle, so I'm going to say 2 times happened, right? So I just sum the value, the sample returns up, and then divide it by 2, right? So that was exactly the same thing we did in chapter 3, first thing that when we wanted to start with Monte Carlo, right? Now, we can have a mini batch, right? And you can repeat the same idea or extend the same idea on a mini batch, right? So you go on every single trajectory, you average on that trajectory, and after doing that, then this is one average that you have, then you can average it again over your whole batch, right? So you can write it down in this form, so you could say for one trajectory, again, every single sample return that I have is one estimator of my value. So how can I find an estimator of the value function at one particular state? Well, I'm going to see how many times this state has happened in one trajectory. I add them up. Also, I just add this up over all the trajectories inside my batch, and then I divide it by the number of times that I have seen in total, right? Just basic averaging, nothing special, right? Everybody's clear? So this guy that you have, you can just replace it as a value estimator, right? So you might say that, okay, I don't have the value function itself, but I'm going to replace it by an estimator, right? And the estimator that I have is this dummy estimator that I showed you, right? Everybody's cool, right? So you can do this, you can implement this algorithm, and this is going to not work, right? Obviously. So you do not expect this guy to work, obviously, because simply you have too much probably states in your environment, and then you're not going to see them so many times. Probably many states you're going to see once in one single trajectory, never ever again. And then doing this, obviously, is tabular, is not going to be efficient, right? But theoretically, if you have a giant mini batch, if you have a very long trajectory every single time, then you are seeing enough number of samples that you can estimate, and this guy should work, right? Everybody's cool, right? Now, one thing that I also mentioned again in chapter 5 is that here, as you can see, you actually do not need really to work with any action value function, right? So you don't need to estimate the action value. You don't really care what action your policy network has done, because your advantage is only depending on the value of the states, right? So this is a kind of improvement as compared to estimating directly the action value function, because the space of things that you're estimating is smaller. But yeah, again, this is not going to work really in practice. So doing that is not going to give you very impressive performance. But the thing is that those samples that I told you how to collect, you can take them as a sort of sample values for a value network, which can be trained alongside with your policy network, right? So you take them as the samples for your value network. You would say if that state goes inside my value network, then I need to see this particular sample or something close to that at the output, right? And then you train this guy by, a stochastic gradient descent. You're going to get something, and then you use that value network, right? That value network is going to give you a kind of smoother approximation of the value you need, okay? So this is not going to work. The reason, well, you very well know the reason. The reason is that, well, this is a giant space. You cannot really do it by a tabular approach. And the solution, is simply to just use a value network, right? Just a function approximation using a value network. And let's do it together, right? So now, one question. If I want to put a value network here, what kind of network do I need? Do I need a V network or do I need a Q network? A V network, right? So you can just use a V network. You don't really need a Q network, right? Because you just need to play with the values, right? You look at this state, it's going to give you the value. You don't really need to know the action value function here. So you can use a value network simply, and every single time you're going to give the representation of the state, right? To your network, I am here. The representation is, for example, my coordinate. I'm going to give it to my value network, and it's going to give you some value, right? And what you want to do, you want to keep on updating this guy alongside with your policy network, because every time this guy should somehow match itself to the policy that you're playing with, right? If you don't do that, then this guy could be something totally detached from the policy that you're playing with. So you can have your value network. This value network is just replacing exactly what you do with Monte Carlo. And then, of course, the data set that you need are the samples that I told you are going to collect, right? For every single time, or every single trajectory, every single state that you see, this is having one label. And that label is simply the sample return that you get, right? That sample return is the state, that sample return is the estimator of the value of the corresponding state, right? And simply, you get this data set, you try to train your model, then this is going to somehow give you an estimator of the value. And it's also, again, same story as before. It's also able to give you an estimate for those states which you have not seen before, like you are just playing and you get into that state out of the sudden, right? Okay, so how we can train that guy as before. So you're going to give your state every single time on every single trajectory. You give this state as an input to your value network, right? And this is going to give you an estimate as an output, and then you want this output to be close to the estimate, right? So subtract it, squared, and then you add it up over all trajectories that you have inside your mini batch all the time over the trajectory, and this is going to be your loss function. You try to minimize this guy, right? And every time you just minimize this guy, you update the value in the parameters of the value network, right? So everybody's cool? Yes?
How do you calculate or estimate here? Is it the Monte Carlo estimation?
This V hat is the sample return. Just the sample return, right? So you don't really need to do any Monte Carlo anymore, because if you have one state here and you get one sample return, right? This is one label, and then later you see the same state with another label, right? And your network somehow starts to learn that it needs to interplay somewhere between them, right? So you don't really need to do the average. Questions? Everybody's cool? Okay. So that would be the main idea, right? So this is the one very basic actor-critic approach that you can do. This is basically the baseline policy gradient method when you are doing an estimation of the values as well, right? So you start with one mini batch. You're going to sample a bunch of trajectories. For every trajectory, what you do, you go inside and then you estimate your your advantage, right? And how do you estimate? Well, this is the immediate reward you see in your trajectory plus discount factor times the value of the next stage, right? What is the value of next stage? Give it to your value network, right? So it goes inside the value network. It's going to give you one estimate, right? And then minus the value of the, oh, this should be ST. Sorry, here is a typo. This is ST, the second one, right? Obviously. So then you would say, okay, the value of the current state that I have, I also get it, and the difference between these two, this is going to be your advantage. If you have advantage, you can compute the sample gradient of your policy network, right? This was PGM. So, sorry, policy gradient theorem. You get this advantage, you multiply it to this to the gradient of the log likelihood, right? And now, the next thing that we need to only care about is that how we're going to update this W, right? And for updating the W, we're going to do something simple. Every time we get into one of those samples, one of those trajectories, you just compute the value of, or sample return for every single time, right? So every time you come here for this one trajectory, you're going to say, okay, S0 has a sample return which is R1 plus R2 towards RT, right? Then S1 has a sample return which is R2 plus R3 and so on, right? So every single of them has one sample return, right? And you simply take it as your value estimate, correct? And then you get this value estimate. So for every single time, you have a value estimate. And then once you're over with the trajectory, you just take it as a kind of estimator or label for your value network, and then you update your value network using, for example, a stochastic gradient descent, right? You got the idea? No worries, I'm going to show you how exactly you should align the updates. But actually, we can merge the updates together. We're going to talk about that. But you got the key idea, right? How the updates is happening. So every time you go over a trajectory, you get sample returns. These are the estimator or labels for your value network. You also have the gradients of the log likelihood. These are the sample gradients that you need to update your policy method, right? Policy network, sorry. And then the thing that you do once you are over with the trajectory, you update your policy network, and then you also update your value network doing one or maybe multiple steps of gradient descent. Okay, cool. So one thing here is that I think I mentioned this in chapter 5, but there is one key observation here which helps us to somehow merge these two updates together. And that key thing is that the advantage that you are computing is indeed an estimate, a TD estimator of the error that you have, right? So I think I mentioned it quickly before in chapter 5, but we're going to see it here, and we see how we can apply this observation to our update loop inside the Actor-Critic method. So the key point here is that since I have a value network, now I can use temporal difference, right? This means that every single time as the estimator of my value, I'm not going to take the sample return completely, right? The sample return, it means that I start from S0 and I say R1 plus R2 towards the end, right? This is the sample return for S0, right? And I told you take this guy as the label, right? But you could also use temporal difference. You would say, what is the value of S0 or an estimator of this guy is the sample reward that I get plus value of the next stage, right? That was temporal difference, right? Because of Bellman equation, right? So what I could say the value at time t, I could estimate it to be the immediate reward that I get plus discount factor times the value at the next state. And since I have a value network, what I can do, I just get my next state, give it to my value network. It's going to give me what I need, right? Everybody's cool, right? So I can do that. Now, if I do that, then what I want to use this guy lecture to just update my value network, right? This guy, this value v hat, is only used to update my value network, correct? But now you have this advantage, and the advantage is simply the same guy, so it's v hat as you see above, right? Minus the value of your current state, right? This is the advantage, right? And this was coming because we wanted to unbias our action value, right? Now, the key point here is that if you take this guy, right, this value v hat that you have, and you put it inside the loss function that you are using to update your value network, then the things that you see inside this are essentially some of those advantages, right? So if I take this guy, I mean, it doesn't matter v minus this one or the sample minus v, right? It's the same thing. It's the squared, right? Now, if you look at this guy, v hat minus the value at the particular time t is v hat, this guy, right, minus the value at time t, which is this guy, right? So you see, you have your sample returned by td, this guy, minus the value of your current state. This is the same argument that you have here, right? And this one is nothing but the advantage, right? So the advantage itself is actually giving you an estimate of that error term you want to minimize, right? You see it, right? So now we can use this fact to somehow merge the both updates into one simpler loop. And then this is what we're going to do. So if I want to compute the gradient of this guy, right? If I want to take the gradient, how do I compute it? Well, we have done it before, right? We have this summation which we don't care. The thing that we care about is this argument, right? So you have something squared is going to be 2 times this guy times the gradient of whatever is inside, right? And the gradient of the thing inside is the gradient of this one, which you can compute by backpropagation, right? This is your value network, correct? The thing left is 2 times this guy, right? So if I open up the gradient of this loss function that I want to minimize for my value network training is going to be 2 times this expression, right? The value of the current state minus the estimator times the gradient of my value network, right? Correct? So we did this before. We called this minus delta, right? Delta was the difference between the estimate and our actual value, right? And we said we're going to update with this one. So every time that we want to update, we're going to get a learning grade. Here it's beta times this guy, right? And this guy has been maybe summed up over multiple time steps, multiple trajectories. Again, we don't care, right? The thing is that we have a beta average of those deltas times the gradient of the value network, right? Now, the key point here is that what is delta? If you look at this one, what is delta? Delta is the same thing as UT, right? Delta is essentially estimator minus the value at the current state that you have. Delta is nothing but TD, right? So the estimator is this guy using TD, and then delta is basically your estimator minus the value network at the current state, which is basically advantage, right? So the advantage is actually estimating this error term delta that we have when we want to update. So when you are actually computing advantage, you're doing this, I mean, you are getting what you need for updating both policy and value networks, right? And this is a kind of interesting observation which we can somehow implement inside our training loop to just merge both updates together, right? So this is what I told you before. So very key observation. Advantage is an estimator of the TD error, and you can simply use it in practice. This is what we do always in practice. So how can I use it now? Well, I could say that, well, I get into the loop, and then I'm going to sample this trajectory, for example. And now that I sample this trajectory, I already have my value network, right? So for every single time step, I'm going to compute the sample advantage, giving the next return immediate reward that I get, plus next value minus the current value, right? I have the value network, I can compute that, right? Now this UT is going to be the advantage and the error term for the value update. So what I'm going to do, I'm going to just estimate the gradient of every single network, right? The top one is the gradient of the policy network, so I simply use the policy gradient theorem to compute it, right? I would say advantage at every single time, multiply with the gradient of the log likelihood at that time is going to give me one time step of my policy gradient, right? And I just aggregate it over the whole trajectory. This is one estimator, right? And one thing that I can do, I just go over my trajectory, right? At first time, then add it up to the second one, and so on, right? So this is what I get on the trajectory. This is the estimator of the policy gradient, right? And I can do the same thing at every single time. I am just computing one advantage, which is basically the same error that I need for my policy update, so my value update, right? And I'm going to just backpropagate over my value network to compute the gradient of the value network at that particular stage, right? And then I just aggregate it over all the trajectories, right? Now you have two things, two gradients. So you take those two gradients, you use two different learning grades maybe, and you update both the together, right? Everybody's cool? Yes.
Sir, I guess it's more like I get the math. I guess right now I'm thinking of advantages like how much better this action is than the others.
Yes.
And seeing it as like the same thing as how off an estimate is kind of like how that sort of seems backwards.
Well, you could say that, I mean, you could somehow justify it that if you have the optimal policy, then essentially it's going to look like either deterministic policy, or if it is not deterministic, it's just doing these actions which give the same value, right? If you have optimal policy, right, it's either deterministic or you are doing an action which has the maximum value. Maybe you have multiple of them, right?
Yes.
Now, this means that it doesn't matter what you do in your policy, you always get the maximum value, right? So this means that you're going to have zero advantage, right?
Yeah.
Yeah, is the reason, right?
But in that case, you also have, like, your estimate of the value is also perfect, so it's going to have zero error?
Your estimated value is going to have zero error, right?
So in the same way that there's zero advantage, there's also zero error?
Zero error in the value, right, definitely.
Okay.
That could be the case. Yeah, that should be the case, right? Yeah.
Because your value network is perfect then.
Right, because your policy is optimal, yes, and if your value network is also perfect, it should just give you the right value, which is the maximum value always when you play, right? Yeah, that's it. That's correct. That's correct interpretation.
Well, that made it make more sense.
Okay.
Thank you.
Questions? Okay, so this is the most basic version of the Actor-Critic approach, and this is what people call it advantage Actor-Critic, or A2C, right? One of A's come from advantage, the other one actor, right? A2C algorithm, right? So the most basic approach that you can use both networks to just update, right? And now, here what I have shown you is actually a single trajectory form. This means that you are going to update your value and policy network after every single trajectory. Well, you can have online version, you can have mini batch version. What you have in practice, usually you have a mini batch version. And online version, you usually don't have it because it's not very stable. But still, you can think about this, right? What you can say that I update my policy and value network after every single time step in my trajectory, right? So this is like the control problem you had, right? Every single time, you just compute the advantage. Using that one, you're going to estimate one piece of your gradient for value and one piece of your gradient for your policy, so you don't complete you don't finish the trajectory, you just update, right? And then you're going to go for the next point inside your trajectory using the new policy, right? So the next action that you do is done by the updated policy, right? And then you update your value network to somehow estimate that guy. But you can guess that this guy is not going to be very stable because the frequency of the updates you are doing is so fast that your value network is not really able to capture the policy at all, right? It does not have enough samples to just update it, right? To get it, just starts to jiggle around only. Okay, so, and this guy is the mini batch version, which is more practical. Like in practice, you usually do that, right? So you're going to sample a mini batch. Once you sampled, you're going to get advantage for every single guy inside that trajectory. You update, and you keep these guys. And then once you're over with the mini batch, you average over the mini batch, then you update your policy and value network. That makes more sense, right? So this is the the one which is going to function at the end of the day. Yes?
Do you do sample replay with this?
Sorry?
Do you do sample replay with this?
Yes, we're gonna do it. I'm gonna explain that. But you need to pay attention on the updates of the value network. This is the only difference. Yeah. But you definitely do that, right? Usually how you implement it, you're gonna just get your policy, you sample with it, like a bunch of trajectories. So you have your mini batch, or not mini batch, the complete batch actually. And then you start updating, right? And every time you want to update, you just randomly take a bunch of trajectories as a mini batch, and you update. But when you update, you get your new policy, right? Then you reuse whatever you have inside that batch using important sampling. By doing that, you somehow make sure that you are not actually getting any significant bias. But then after updating for a couple of epochs, then you stop. You just throw away all the batch, and you just get a new fresh batch. Yeah.
So the important sampling that you just mentioned, that will be the ratio probability of an action from the old one with the ratio of probability.
Exactly, exactly. So you do know that I have sampled with this particular policy. So you do know that policy at that of the sampling or the density of the sampling policy. And then you also get your updates, or your target is your current policy network, which is getting updated. So you always consider that as well inside your samples, right? Questions? No question? Okay. So, yeah, one idea that people have also implemented, and for many applications, not many, but some applications it really makes sense, is the idea of just using shared network. So what is the shared network idea together? The point is that when if you are really playing optimal, that playing optimal or that policy is actually the policy which makes the value optimal, right? And this means that what you learn for value is somehow related to what you learn for your policy, right? Then the question was that why don't we put one giant network which has multiple heads at the output, and one of the heads is giving us the policy, the other one is giving us the value, right? So you have just one network. You don't really need to have separate networks, right? And yeah, you can do that. Then this is a shared network. So you have your representation. You can have a representation of the state and action together going inside your giant network, and gives you the estimate of the value and the policy itself. But typically what we do, we're going to just give the representation of this state, and then at the output we are going to have one probability distribution to sample from, and also one value function, right? One value calculation. So if you want to think about that, I'm going to show you the visualization. This network is simply just one giant deep neural network, right? And it's going to have multiple heads as the output. One of the heads, basically two heads, right? One of the heads is just policy. The other one is just giving you the value. And if you want to visualize it, it's something like this, right? So for example, if it's just playing some computer game, it's going to take the input. Maybe it's the image or multiple images of that one frame of your computer game. This is the state that you're in, right? And this is going inside the neural network. This is going to process it up to some point, right? And at the very end, when you have your fully connected layers to compute the output, you're going to just have two heads, right? One of them is just computing all of those features into for example, categorical distribution, right? This one, which is giving the probability of every single action that you can do, right? The other one is just giving you one single output, which is the value of this state we have seen, right? Correct? So that guy is, I mean, it might be more stable if you really can manage to have this nice architecture, right? Depends on the application that you have. But for instance, if you have a discrete space of actions, then this could eventually work fine, right? Because it's not a very complicated thing. And you can guess that every single action, I mean, at the end of the day, this guy should be one deterministic distribution with the highest probability corresponding to the one which is maximizing the value. So it makes sense that you use the same set of features for them, right? OK, so now one thing when you're using a shared network, one question that you might have is that, well, if I have a policy network and if I have a value network, then I'm going to use the policy gradient theorem to get the gradient for the policy network and update. I'm going to use my gradient descent on the value loss that I computed to update my value network, right? But now I have just one giant network, right? And I need to just minimize one loss, right? There is no, I mean, there you have two different losses, right? For two different networks. Now you have one loss. How you can combine these two different losses? Well, you can simply add them up, right? And maybe you do not simply add them up with the same weights. Maybe you just add some other weights, right? So for example, you say, this is the expected value I'm going to get out of my policy. This is what we tried to maximize when we wanted to do policy gradient method, right? And this ended up with the policy gradient theorem, that J. And then you have the other guy, which is the loss of the value network. Now, both of them depend on the same set of parameters, right? So same set of parameters, the same neural network is computing both of them, right? So how you can define your loss? Well, you can get the loss of the first one added up with some coefficient times the loss of the second one. And that coefficient, you simply need to tune it in a way that both losses just get in the same range, right? If one of the losses in the order of 10 to the power minus 3, the other one is in the order of 10 to 10, well, they do not match, right? And you need to just scale one of them up or down to just get in the same range, and then they just get minimized together, right? So you can do that, and then again, when you write down that thing, it's going to only depend on the advantage. This is the same thing that we observed before. And yeah, you just compute the gradient of this guy, and the gradient of this guy is not, no magic here. So it's the gradient of the policy like the log likelihood, which we use for the policy update. And also, this is the gradient of the value part, right? So again, we use for update of the value network. So basically, the gradients you're computing are running or backpropagating over exactly the same network, right? Only the last head gradient is going to change inside your chain rule, and you're going to add them up together to update, right? Everybody's cool? Questions? Great. So if you just merge them together and make a shared network, then you're going to have the same algorithm as before, but now you're going to have just single gradient, right? So you sample, you compute the advantage using the value head, and then to compute the gradient, you're going over your trajectory. Every time you're going to get the gradient of the log likelihood plus the gradient of the value head together, and then you multiply it with the corresponding advantage, right? And you just aggregate all of it over one trajectory. This is one sample gradient, right? You either can update with that sample gradient, or you can do multiple samples in one mini batch to just improve the quality of your sample, and then you update, right? Questions? Now, this guy is a quite robust thing. Like, if you have a fair mini batch, and if you're able to sample from your environment easily, then you can actually train this guy. This is going to work. Questions? No question?